All right, welcome to module number 31. The topic here is going to be on shrinkage. And we saw in the subset selection module that we often want a sparse solution, a solution that contains a lot of zeros. And that is equivalent to throwing out many of the columns of the matrix. And in some cases, there's going to be a minor extra error that comes in. And the advantage in terms of a sparse, a low complexity, a simple solution, perhaps easy for our hypothetical cardiologist from an example that I described, that may be beneficial. That may be a minor error might be worth the cost. Or alternately, there may be situations where you really believe that there are a lot of zeros in the system. For example, the communication problem. But yes, it may introduce large errors. So that's in the general case, this needs to be handled with care. And shrinkage methods, they modify the beta, the set of estimated parameters, in a more subtle way. They don't kind of butcher it towards zero. They shrink it. They pull it gently towards zero. So one way of doing that is ridge regression. It penalizes a large beta. So whereas the regular least squares, what it does, it performs an argmin over the betas of y minus x beta squared L2 norm, where x is the matrix, y are the noisy measurements, and beta are the coefficients. Here we add a new term. We penalize by lambda times the squared L2 norm of the vector beta. Lambda is a Lagrangian type of variable. Large lambda, small lambda, they can pull us to two or different solutions. And basically, with this type of modification, we don't want a large energy beta. Okay, so we're penalizing larger values, and this pulls us slightly towards zero. How do we implement this? One way to implement it is using a modified pseudo-inverse. So it can be shown that whereas the regular pseudo-inverse is x transpose x, the inverse of that multiplied by x transpose, here we add lambda I to the x transpose x. And this minor modification, again, so this is closed form. So this is can be calculated. It's a linear approach, meaning that beta hat is a matrix times the y vector. That's it. And just as a quick comment, I here is the identity matrix. All right, so this brings us to the LASSO. Ridge regression adds an L2 penalty term for the energy in the betas, and the LASSO, or least absolute shrinkage and selection operator, gives an L1 penalty. So one way to incorporate the LASSO is that we're looking for the beta vector, the argmin, meaning the beta vector that minimizes y minus x beta squared L2 norm, subject to the L1 norm of beta being small enough. Now, what would small enough mean? If t is large, t is a threshold, THR for threshold. If t is large, this constraint is meaningless. It doesn't really constrain us. If t is small, on the other hand, it means that beta has basically smaller values. And that would mean that many of the coefficients are driven to zero. Now, I'd just like to note that it can be shown through the optimization ideas that we've discussed already that this optimization problem can be reformulated using a Lagrange multiplier as follows. We're looking for the argmin of y minus x beta, the same expression as before. So let's call this expression one plus lambda times the L1 norm of beta, which would be expression 2. And lambda would be a Lagrangian multiplier, and different lambdas would yield different types of solutions. Now, there are different fast algorithms to implement the LASSO. So the LASSO is a formulation, and you can solve it, for example, with a convex optimization. You can solve it with gradient projection for sparse reconstruction, or GPSR, which was a work by Noack et al. Or you can also implement it, in some cases at least, with approximate message passing, or AMP, which we're going to revisit during the sparse signal processing part of the course. So let me give you an example, work of mine from 2006 with my colleagues Shri Sarvatham and Rich Baranuk. And in this example, I'm going to demonstrate that sometimes for structured problems, when beta is structured, we can actually do quite well. So the challenge here is, why would we think that we can estimate a sparse beta? Is there some advantage to a sparse beta? So if we just pause for a moment, you can realize that the search space for all possible betas is much, much larger than the search space for betas that are primarily zero. So we have a smaller design space, a smaller search space. Does that help us? So LASSO can drive many of the coefficients to zero. Is that reasonable? So now let's revisit a linear problem, y equals x beta, and let's assume the following. First of all, there was no plus z or plus n here. There is no noise. Secondly, the beta are real valued. It's not integers or something like that. It's not like, recall that we had in the communication problem, -1, 0, +1. Here, arbitrary beta. And finally, most importantly, sparse betas. The beta vector is dominated by zeros, and during the sparse signal processing material, we're going to justify that by realizing that sparsity is a concept that for many types of realistic, real-world signals, sparsity actually happens with respect to a reasonable basis. Okay, so let's just keep that in mind. Sparsity is justified for many types of real data. So we're going to assume that beta is sparse. And under this assumption of beta is sparse, no noise, beta is also, well, the non-zeros and are real valued, recall from linear algebra that there must be as many observations as unknowns. So X is a matrix. Okay, so Y, a vector, is X times beta. And here, beta perhaps is of length m, and y is of length n. The number of observations is n, and the number of unknowns is m. And you could flip the notation. I'm just trying to say that linear algebra tells us that the number of observations n must be at least as large as the number of unknowns m. However, and this is an important point, if beta contains structure, one type of structure is sparsity. Another type of structure, as we said before, integer valued, or maybe it's in a discrete set, or when beta contains structure, you can actually pull this off. Okay, you can pull this off with a smaller number of measurements. And smaller number of measurements is a good thing. It means reduced resources used to solve the problem. So let's see this through an example. And again, this example is really an algorithm from 2006. And to put things in perspective, 2006 was not really that far ago. So what I'm going to describe was novel in 2006, okay? So here we have a linear inverse problem. Y, 4 numbers, a vector of length 4, is the matrix X with 4 rows and 6 columns. And beta is the unknown vector, and we have 6 question marks. Now you'll note that X is a completely binary matrix, so it's not an arbitrary matrix. And we're going to see that with only 4 measurements, we can estimate correctly 6 question marks, 6 unknowns. So how do we do that? Let's look at this first measurement, which we're pointing to with the red arrow. It's a 0. And 0 measurements are helpful. It'll turn out that for these types of problems, sparse beta, these matrices that are binary, 1s and 0s, oftentimes we're going to have a 0 measurement. And what does it mean that we have a 0 measurement? So let's think about this carefully. This measurement is the outcome of an inner product between X and beta. And in this row, we only have 1s at locations 2 and 3. Therefore, the rest of the locations 1, 4, 5, and 6 are not measured. So we're not measuring 6, we're not measuring this guy, not measuring this guy. We're only measuring beta 2 and beta 3. and beta 2 plus beta 3 is equal to 0. Now recall, beta is sparse and real valued. So what does it tell us if there's a 0 measurement? So thinking through this, one possibility is that beta 2 is equal to beta 3, and they're both equal to 0. Another possibility is that beta 2 is equal to negative beta 3, and they're both non-zero. Now recall, beta is sparse, so there are a lot of zeros. So this is plausible. I'll put a check mark. Beta is a real value. The non-zero is a real value. Therefore, beta 2 and beta 3 being opposite in sign doesn't make sense. Like 3.725 and minus 3.725. Doesn't make sense. So the real explanation here is that beta 2 and beta 3 are equal to 0. So moving on, what we did here, we marked zeros in locations 2 and 3, and now everything related to the matrix X in columns 2 and 3 can be marked as solved. So I put this in purple, and row number 1 has been resolved. We understand why this 0 measurement is 0. And this is graph reduction. We've reduced the remaining size of the problem. Earlier we had 4 measurements, 6 unknowns. Now we have 3 remaining measurements and 4 unknowns, a smaller problem. So the next step in this algorithm, one step is to identify 0 measurements. The next step is oftentimes in this algorithm we have matching measurements. So here these 2 measurements are both 1. So what does it mean that we have matching measurements? So again, let's try to understand what happens here. These parts of the matrices have already been marked off because we understand that beta 2 and beta 3 are equal to 0. So we know here that for measurement number 2, y2 is equal to 1, and it's equal to beta 4 plus beta 5. And we also know that y3, which is also equal to 1, is equal to beta 1 plus beta 5. Now again, recall, the beta vector is sparse, contains a lot of zeros. The non-zeros are real valued, arbitrary. So one possibility is that, let's say B4 is 2 and B5 is negative 1 and B1 would be whatever. Well, if B5 is negative 1, then B1 and B4 need to be the same because both of them plus B5 give the same value of 1. So that doesn't really make sense. A much simpler explanation is as follows. B4 and B1 are both equal to 0, all right? So we know that's plausible. And B5 is equal to 1. So 0, 0, 1. That's the type of information that a non-zero measurement, matching measurements, matching non-zeros give us. So now, again, we've performed graph reduction, and we are down to, we've solved beta 1, beta 2, beta 3, beta 4. Here I denoted by y equals phi x. You know, notation is notation. There's one missing location, and there's the first 3 measurements have been marked off. And what is this last value? Well, 4 equals to 1 times the question mark, so the answer is 4. Actually not. So recall that x5 plus x6 is equal to 4, and x5 is equal to 1, and if 1 plus x6 is equal to 4, that means that x6 is equal to 3. So the point that I'm trying to emphasize here, during the graph reduction, when we identify a non-zero measurement, actually it's advisable to compensate for that in the remaining measurements. Okay, so we perform graph reduction while compensating for the unknown measurements as we uncover them. So overall, what we succeeded doing here is we succeeded solving 6 unknowns with 4 measurements. We did that by specifically utilizing the 0 measurements and the sparsity of the beta vector. And we also understood that when there are matching measurements, because there are a lot of zeros and the real valued non-zeros are, well, real valued unstructured, matching measurements were, again, they provided a lot of information. So this resembles solving a Sudoku puzzle, but the beta vector is sparse, there's no noise, and we also assumed a binary matrix. In real world problems, beta may not be exactly sparse, it may be close to sparse, there may be a lot of small non-zeros, but not exactly. In real problems, there will probably be some noise, and also sometimes the matrix will be binary, sometimes not, it depends. So this can be expanded to noisy data, for example, by evaluating almost matching measurements. So we had 2 measurements that were both equal to 1, and imagine that one measurement was equal to 0.9 and the other was 1.05. So they're close. And that's a technique that we used in the following paper from 2014 with my 2 collaborators, Yenting and Deanna. So overall, we're going to study more powerful algorithms using sparse signal processing during that section of the course. But the idea that I'm trying to already give you is that even if you've been taught in linear algebra that we need more measurements than unknowns, if you have structure in the beta vector, that is not necessarily true anymore. So that'll be all for this module, and we'll continue next time.